Really happy to welcome Mike Hicks back to MSR to give us a talk here. I'm especially happy because Mike is my PhD advisor, and it's great to have him here again. I think you all know Mike very well.
I said I just never go away. I'm always there to.
Right, yeah. So all of you probably know Mike pretty well. So I was thinking about like a couple of things I could tell you about Mike that you maybe don't know. And it's well, so one, he's a pretty badass prog rock drummer.
Badass.
You see him like tapping really fast, and when you're talking to him in meetings, like whacking out some crazy rhythm on the side. That's cool. But also maybe more technically, I think Mike was one of the original designers of the Cyclone programming language. In particular, it's linear typing discipline, among other things. And these days, that was about 20 years ago already, I think, by now.
15, yeah.
Well, 2000-ish?
2003, yeah.
Okay, so getting there, okay. Things like linear types, I think things like Cyclone back then is like way ahead of its time. And now these ideas are seeing, major adoption in things like Rust and so on, all the basic mechanisms for aliasing control in low-level programming languages, ideas that Mike came up with several others a long time ago. So it's great to have him here.
Thanks.
Hear about testing.
Right, here for the Deep Spec workshop at PLDI. Okay, thanks, Nick. That was probably the best introduction I've ever gotten. So high bar for the next person. Okay, so this paper is with these wonderful people. So Leo is a postdoc at Maryland now. Benjamin is at UPenn. And Leo was Benjamin's student, and now Leo is my postdoc. And so I'm going to talk about how we can do the Reese's Peanut Butter Cup thing with fuzz testing, coverage-guided fuzz testing in the style of AFL, and property testing in the style of QuickCheck. Okay, and so that's the question. Is it a good idea to combine these two things? And the answer is, of course, yes, or I wouldn't be standing here. So let's talk about what they are. So fuzz testing is extremely popular these days. It's a form of random testing that's surprisingly dumb. It's slightly smarter today. The most dumb incarnation of it came about in the early 90s. Bart Miller is credited with starting it. And basically what they found is if you send lots of random inputs to Unix utilities, they would crash, and those crashes would reveal important bugs that they had. Things have gotten a little more sophisticated. Actually, it's a little sad. You can still do the really dumb thing and find bugs in programs today. But modern fuzz testers like AFL or libfuzzer are a little bit smarter in the bit level mutations and such that they do to generate these particular inputs. That is, they look at what's called coverage. So looking at the layout of choices you can make in your kind of fuzzing, you could do the Bart Miller thing that's completely random here, no user effort, but maybe in the broad scheme of things not as good at finding bugs. And then you could also do something like here in the upper right, as done by many tools these days, where you have some kind of custom input generator that tries to be smarter about the inputs that it sends. So instead of using completely random garbage that you send to a program, maybe you have a grammar so that you know that, it accepts XML files, so I should send it only XML inputs, or it accepts JSON or something like that. And so I'm going to get better results rather than having my inputs rejected all the time over and over and over again. If I adhere to this grammar, then I'll do a little bit better. Now, the most popular version of fuzzing today, I believe, is this style that's exemplified by AFL, which is no user effort at all, same as this, except that there's a little bit more smarts involved in what the fuzzer is doing, and that's watching how the program executes to keep track of what branches and edges and control flow blocks and such that it reaches, and using that information to be a little smarter about deciding what the next input should be. You can also imagine enhanced fuzzing that uses more sophisticated techniques. So for example, as Patrice Godefroy pioneered, using symbolic execution in combination with fuzzing, exemplified by the Driller paper, which was a few years back, where you do random fuzzing for a while, and if you notice that you're starting to get a little bit stuck, you're not going to new control flow paths or whatnot, you can use symbolic execution to try to find a new control flow path and then revert back to the more dumb fuzzing. And that also seems to work well, and it also has this nice feature that it requires no additional user effort to employ it. Okay, so the kind of fuzzing I'm interested in at least for step one for the combination with QuickCheck is this AFL style. So let's look more carefully about how it works. So here's the program that I'm testing. What I'm going to do is I'm going to have an initial seed file. So in the limit, you can imagine that the seed file is empty. It's an empty file. So maybe this program is Acrobat Reader, and it's expecting PDF inputs, but I won't give it a PDF. I'll just give it an empty file. And then Acrobat Reader will reject that file, and as a result, that information, the rejection, will go back to the fuzzer, and the fuzzer will then try to figure out, okay, how can I learn from that rejection to try to come up with a better input that gets me closer and closer to finding a bug. And what it tries to do is it looks at the input and it says, did I see any new paths that I haven't seen before, any new control flow edges, any new basic blocks? And if so, I'm going to retain that input file as the basis of a mutation. And those mutations are going to be things like, well, let's double the contents of the file and then XOR half the file with the other part of the file. Let's slop off parts of the file. Let's flip some bits. Just do very weird, interesting things. And then we'll use that as the new seed and then feed it back in again. And then see, well, how many new paths were created? Were any new paths created? If the answer is no new paths are created, we'll just throw away that new mutated seed and we'll stick with the one that we already had. And there's a scheduling algorithm that sort of decides how long to stick with one particular seed and how often to try to generate something that's completely new. So goes around for a long, long time. So many fuzz testing tools will work by a fuzzing campaign will be at least a day, if not weeks or longer, right? And here at Microsoft, the fuzzing is used regularly for Microsoft products, and basically the fuzzers are running all the time, trying to find wacky inputs to send to PowerPoint to get it to crash. Oh, this is animating, sorry. Okay. What's QuickCheck? What's property testing? So property testing was popularized by these two gentlemen from Chalmers for Haskell. And the idea is that you, instead of writing, if we step back and we think, the tests that I write to test my program, oftentimes they're not in and of themselves interesting. Rather, they're instances of some high-level idea we have in our heads, right? So if we write a sorting function, what we might do is we might say, well, let's look at one boundary case, the empty list. Let's look at a size 1 list. Let's look at a 2-element list where I already have it sorted or I already don't have it sorted. And we think through the way that we write tests to try to cover all of these different cases. So what the property testing tool will do is you can sort of specify these high-level properties logically, and then you can ask the property testing tool to synthesize inputs that satisfy that to see whether or not that property is satisfied. And so that way you're raising the level of abstraction of your testing. You're still considering correctness. You're writing these properties out, but you're not responsible for generating the instances of the tests that push those properties. So it's sort of an attractive midpoint between unit tests and formal verification. You can specify the high-level things, but they're going to be tested rather than proved correct. So for our study, we were interested in a version of property testing called QuickCheck that's for the Coq development environment. And when I heard about this, I thought this is the most brilliant thing ever, which is, what do I do when I program in Coq or an F-star or any of these environments? My goal is to prove stuff correct. The problem is, oftentimes when you write all these definitions down, they're not correct. They're wrong. They don't satisfy that property. And you only realize this when you've put in a huge amount of time trying to figure out whether this is true or not, and then you realize you can't prove it and you have to go back to the drawing board. And that maybe that effort is reusable. Maybe you can sort of get back to where you were quickly, but it also might be entirely frustrating and you have to throw away a lot of work. So the idea of QuickCheck is the properties you want to prove, just state them and then attempt to falsify them by generating random instances that show that that property is wrong. And if you can't falsify it, then that's a good candidate for something that you actually want to prove is correct. So all of this is integrated into Coq. This is a This picture here shows that it's a module in the so-called Software Foundations framework. So you can go online to Software Foundations and go through this module and learn how to use QuickCheck. So this is an example of a property that you might attempt to prove about your sorting function. I have this sorting function. I hope it works. And what I want to show is that when I take a particular input, is it the case that that input is sorted when I pass it to my sorting function, right? Is sorted true? So the way that QuickCheck will work is it will have a generator for inputs that you're universally quantifying over in your property. So in that particular case, we said for all lists, is it the case that sorting that list yields a sorted list? And what will happen is the generator will randomly generate lists, the universally quantified thing, and then it will test that property. Is it the case when I sort it, is sorted holds? And if the answer is, yep, it's good, it'll go right back around and generate a new random input, and then it'll go right back around and generate a new random input. It's not doing mutation. It's generating inputs from scratch using so-called generator functions. Okay, and if it turns out at some point it generates an input that when you sort that input it's not actually sorted, then it will say, whoops, there's a bug in your sorting routine, and it reports that bug to the user. Oh, here again. Okay, so that's great. People love property testing. QuickCheck, that was the Haskell version. It took advantage of Haskell type classes to make generators easy to use and easy to write. But now QuickCheck style property testing is all over the place. They have them for Java and Scala and OCaml and pretty much any language that you can think of, so that's great. Where does this not work so well? Well, it doesn't work so well when you have what we call a sparse property. So if your property has a precondition that has to be satisfied before I'm going to consider whether the thing I'm trying to prove works, for example, my insertion routine there, then what will happen is QuickCheck will generate many possible random inputs, see whether they satisfy the precondition, and if they do not, then it will see whether or not the postcondition is satisfied. And the problem is that if it's very hard to generate an input that satisfies the precondition, you'll just waste a huge amount of time generating tons and tons of inputs that never get around to doing the part that you care about, which is to see whether your insert routine actually works. So what's the solution to that? Well, the solution to that normally is you have to write a smart generator that does a better job of satisfying that precondition in advance. You have to do something that's specific to that property. So naive random testing is here. Basically no user effort. You can use the sort of built-in type classes and whatnot for the generating of your inputs. And it's going to do a fine job of finding bugs. But if I really want to do a great job for sparse properties, almost certainly I'm going to have to do a handwritten generator. And it turns out that writing handwritten generators is not obvious how to do correctly. There are lots of pitfalls in getting that right. So, hey, that looks like the chart that we had for fuzzing. Is there a way that we can, up in the upper right there for fuzzing, we had this so-called grammar-based fuzzers where the inputs that we generated, say for our PDF reader, lots of the time, the PDF reader is just going to throw away those inputs because they're total garbage, and it knows nothing. It notices that it's not really a PDF file, and it throws it away. And so we never get into the guts of the actual Acrobat Reader program to see whether it's rendering PDF files correctly. That's the same sort of problem that we're dealing with here. The way that they solved it in the fuzz testing world was, hey, maybe we can add a little bit of smarts in generating inputs based on our observation of the program execution. I wonder, could that same idea work to solve the sparse precondition property for property testing? Okay, so that's the key insight here. Can we use the same sort of tricks that fuzz testing uses for fuzzing normal executables to property testing sparse properties? And our idea is that instead of using bit-level mutations and sort of one-size-fits-all stuff, what we're going to do is we're going to use synthesized mutations that are specific to data types inside of your property tester. So we'll get to examples of this in a minute, but if you think, for example, of our sorting routine, we have lists. A mutation for a list is take that list and concatenate it with itself. Get rid of the first element of the list. Get rid of the last element. Change one of the elements of the list. Right? I can mutate from a particular input that I started with that seemed to gain some coverage. I like that input, and so I'll mutate from it, rather than the way property testing works now, which is just generate lists from scratch every time you run. Okay, so here's the complicated merged picture between fuzzing and property testing as exemplified in QuickCheck, and we call it Fuzz Check. Okay, so how are things different? So first of all, we're going to start off the process by using the generator. So remember in fuzz testing what happened was some person picked a random seed to start the whole process off with, and then all of the mutations started to happen. And maybe the easier seed to pick is the empty file. For Fuzz Check, what we can do is just run the generator to pick an initial random input to start the process off. Okay? And then that goes into our system under test and our particular property. Now, if there was a bug, we report it just as normal. Otherwise, we check, did we see any new paths using the coverage information that we gathered? If we did see some new paths, this is a good seed to use as the basis of mutation, and we'll throw it into our seed pool. Now we can use our so-called Semantic Mutator to look at that seed and add the list to itself, remove an element, change an element, and so on. And then we can go back around the loop once again to keep on trying this. There's some interesting options that we have here that you don't have in regular fuzzing, which are that if at some point the Semantic Mutator gets stuck and it's not making any progress, you can always just fall back to the regular generator. So in some sense, I think of this as like with classical SAT solvers, when you do reboots or resets, you're working your way down a tree and you're kind of stuck in a local minimum, you can always just start over. So that's not something that normal fuzz testers normally have available to them because they have no way to generate a random input that's sensible. Okay, so let's look at the Semantic Mutator. I've already been waving my hands, so now I'm going to wave them, but I'm going to show you with the pictures instead. So here's a tree-based data structure or graph-based data structure, and I want to consider all of the ways that I could mutate this data structure. So what might it look like? Well, one thing I could do is I could just modify each of the elements at the particular nodes, right? So over there I have 0 instead of 1. For the root, I have a 5 rather than a 4 at this location. So that's one kind of mutation. Another kind of mutation is I could ditch one of the nodes. So I could kill this one, I could kill this one, I could pull out an individual node and just use it on its own. Another thing I could do is I could synthesize a new node, and I could add this tree as a subtree to that new node. Or I could break up parts of the tree and synthesize a new node to add those two parts to. So we see that all of these examples over here. So we have a paper that's on my webpage that goes through sort of formally how do you come up with these invariants. So basically the way to look at it is if you have a data type definition, like you might have in Calc for all the possible variants, there's a way that you can work through, there's a definition in the paper of all of the single stepwise variants for that data type, and our mutator just randomly picks one and uses that. Yeah.
Is that those sets of mutations only for like zero-order data types, like no functions inside?
That's correct. Yeah, it's data types, no functions inside. Yeah. Well, that's a good question. We certainly have not tested with things with functions inside. I wonder if what we would do is just treat the function as a block, as abstract, sure, and then just shuffle it around. Sure, okay. But we have not tried that. Okay, so that's the idea. Let's see how well it works. So what we did was, not quite a year ago, I was a co-author on a paper that criticized fuzz testing evaluation, so I should adhere to my own advice. So we were curious about how to evaluate this in sort of a systematic way. And so what we did was we took a system that we knew was correct, that we had developed in Calc, we had already proved it correct, and then we tried to systematically mutate elements of the system to introduce bugs, and then see how effective ours and competing strategies were at finding those bugs. And that system that we had proved correct was, there were two actually, abstract machines whose goal, the abstract machine's goal, is to enforce non-interference. Those of you who might remember the DARPA crash safe program, the goal of this program was to develop a secure processor where a feature of the processor was to have support that would allow you to prove non-interference style properties, security properties about code that would run on those machines. So what Benjamin and Leo had been doing over the last several years is designing these machines and then coding them up in Calc and proving that indeed they do satisfy the non-interference property that you want them to satisfy. So we had these two machines at our disposal that we could use as the basis of an evaluation. One of the machines was a very simple stack-based machine, and the other was a more sophisticated register-based machine that looked much closer to real hardware. And we evaluated on both of these machines. Okay, and so that's the manual creation of these buggy variants. I guess the way that we try to be systematic about it is that essentially in the machines, there are a bunch of cases when you evaluate an instruction that there are side conditions that are there for evaluating security. And those side conditions you could put in a big table. And basically what we did was we sort of mutated those side conditions to introduce bugs, and then we could see whether or not the fuzz testers would find the bugs. Okay, so we compared our stuff to the purely random case, that is the normal QuickCheck, and we also used handcrafted generators. One of these generators took an entire year to write and was the subject of its own research paper. So that's kind of what we assume is the best you can do. This is the status quo, and then this is where we're trying to make an improvement. Okay, so this is showing you the more sophisticated machine, just to give you an idea of what it looks like. So it's going to have a register file, and it's going to have a heap, and we're going to be able to annotate data inside of our abstract machine with whether it's public, and so the adversary is allowed to see it, versus whether it's secret, and so therefore we're trying to keep that information from the observer. The way that we can state that property is using this ubiquitous non-interference property, and the idea is to say that any values that are labeled as secret, as far as the adversary can tell from observing execution, they should not be able to tell the difference between whether a secret, for example, is actually 1 or whether it's actually 0. So if I have two states that are low equivalent, that's what the little tilde is saying, then those states agree on the public stuff because that's the stuff the adversary can see, but they may disagree on the secret stuff because the adversary can't see that anyway. And what we want to show is we want to show that low equivalence is preserved by execution. And therefore, the adversary is basically never able to tell the difference between a system that has 1 as its secret and a state that has 0 as its secret. Okay, and that property is written like this. It's saying that if I have two machines and those machines are indistinguishable, so they agree on everything other than the secrets, then if I take a step in those two machines, so they evaluate an instruction, then the result is also indistinguishable. Okay, and so then this is a very strong non-interference property because it's considering each individual step of that abstract machine. Okay, and then we're going to compare these three things. We're going to try to fuzz this property to run a bunch of tests. After we seed with the bugs and we run with this particular property, will we find the bugs? Yep.
So I just have a quick question about this. It seems like this particular definition, I mean, it's a super strong definition, but it also seems maybe super helpful for fuzzing.
Oh, really? Okay.
Well, just in the sense that you're going step by step rather than doing end-to-end non-interference, because you could have a gigantic state space that you have to explore to be able to prove it off at the end, whereas here you're just focused on one small step at a time. I'm just asking whether this is a standard approach or if this was maybe biased towards making it easier to prove.
That's a good question. So I think that this property is the property you want because they're worried about well, this is not a non-standard property, I guess, in the PL literature. It might be that that's the reason they chose it. I'm struggling to come up with a good explanation for why it wouldn't be okay to do the other thing. I think it would take longer, right? Because then, step would take a lot longer to run. And I guess the question is, if you had that longer, multi-step, big step function, would you find more bugs somehow? I don't know why you would. I don't know. I have to think about it. It's an interesting question.
From what I understood, the main challenge in trying to fuzz a property like this is to find a pair of inputs that validate the precondition.
This is true, right? I've led you down the primrose path so that you're thinking that way. Well done.
Right?
The problem is that if I can satisfy those,
Yeah.
so let's imagine that I can satisfy, let's say that that part is trivial.
Yeah.
The fact that step just takes a single step means that running a single test is going to be very fast.
Yeah.
Now let's imagine that step takes 2 minutes. I'm not going to be able to run that many tests. So even if I'm really fast at getting past that precondition, fuzzing might be a terrible way of finding bugs. So then the question is, so I'm looking ahead to the next question, which is, well, are we losing anything by doing the single step property? I think the single step property is a pretty standard way of defining an operational semantics for these machines. So I don't think that this is cheating in any way, but I haven't thought about it. Okay, those are the results. So these are the 33 properties, the 33 variants, sorry, of the machines that we fuzzed. The target machine, right, we added these mutations. Each one of these things is a distinct change to the machine that introduces a bug, right? It's a distinct bug. So the y-axis is the time spent, the mean time to failure for finding the bug. So what we did basically is we ran each, I think this is I didn't write this down. This is the average of 30 runs for some period of time. I think somewhere around 10 hours or something like that. Whatever, I guess it's not 10 hours. It's 10,000 seconds at the very top. And we did the average of 30 runs. And we did mean time to failure, the average mean time to failure. So it's an average of an average. Mean time to failure is just, what is fuzzing doing? It's generating a random input. That didn't work. It generates another random input over and over and over again. Failed. I found the bug. How long did that take? When I used the handwritten generators, the ones that took a whole year to write and got an ICFP paper out of it, you can see the blue line's very fast, right? This is a log scale on this side. It's taking less than a second to discover these bugs. On the other hand, the naive case, that's the green bars. Basically, it's never finding the bugs before timing out in every case but 2 cases. Whereas the coverage-guided case, the performance of it is crappy compared to the handwritten case, but actually it's perfectly reasonable in terms of, do I actually want to be able to find bugs? It's somewhere between 10 and 100 seconds in most cases, and then it is taking longer in some cases there in the upper right, and it is the case that some bugs are never actually found. So so we think that's good. If you look at the difference between the bug finding ability and how long it takes, and also in terms of the usability of the system, it's no less usable than the completely random testing. I don't have to write any generators by hand. I do all the same stuff that was there before, and yet I find the bugs a lot faster. Okay, so somewhere on one of the slides, which I didn't highlight, I said that the generator was almost automatic. So actually, it isn't zero user effort. For this particular property, there was one key insight to making this work, which is that generating 2 indistinguishable states, what's the best way to do that? The best way to do that is, well, there's actually several ways that you could do that. In this original generator here, how do I sort of start the process off by generating 2 indistinguishable states, right? So I can only start mutating once I have a seed that will possibly work. What's going to get me to that seed better? So I could do 2 things. I could generate 2 random states, and I could ask whether they're equal. Or I could generate 1 random state, make a copy of it, and mutate the other one, and then ask whether or not the 2 things are equal or indistinguishable. This is way better. You're not going to waste all kinds of time generating 2 random states, not finding the right thing. And this was an insight that was in the handwritten generators paper. So basically for the Fuzz Check case, what we do is we do write a handwritten generator that just works like this, that just says take 1 state and then make a copy of it, and that's it. Take those 2 states, they're literally the same thing, and then mutate that instead. That's what starts off the process. And then Fuzz Check takes it from there. So if you wanted to have the completely naive case, Fuzz Check would also not do as well. But I should say in the other direction, even if you used this particular case, which we did do for the purely random case, you're still screwed because there is no notion of mutation in the purely random testing case. So you can't use this approach. You're forced to use this approach. Okay, so I want to point out that there's another way that you could combine coverage-guided fuzzing and property testing, and that's exemplified by some work that's called Crowbar. Actually, there's another paper that just came out in ISTA, which I'll talk about in a second, called Zest, that does something similar. And the idea here is that instead of doing semantic mutation, what you do is you focus your mutation on the source of randomness into your random generator in the first place. Okay, so here I have a normal property tester, and I have my generator and my system under test and so on. And that's the same thing as before. And normally what happens is the random API that you use for normal random testing is actually random. You like sample from dev random or something like that, so you get some random bits every time that are the basis of you generating a random input. However, you don't actually have to do that. You could actually pull away the real random, the back end of the random API, and instead you could put a file there with a whole bunch of random bits, and then you could mutate the file so that now your source of randomness is this file that its bits that you draw coin flips from continuously change. So that's what's happening in Crowbar. It's looking to see whether it got new paths, and then the seed is this file of randomness, and it will mutate that seed, feed it back into the random API, and then just continue going. So this is a way that you can much more easily retrofit coverage-guided fuzzing into an existing property tester. You don't have to implement this semantic mutation idea that I was showing you before, where I look at actual trees and I mutate the trees. Instead, I'm just doing bit flips and everything else that AFL normally does, but now on this random file. Okay, so in our paper, I'm not showing it here, this doesn't work as well. I think I have a slide. Right, I guess this doesn't work as well. Why doesn't it work as well? I mean, I think maybe you can imagine the inside of why it might not work as well. The problem is that when you're doing semantic mutation, you have some sense of the structure of the data you're mutating, and you can mutate it in a sort of semantically meaningful way. I can take one tree and turn it into two trees. And why might that matter? Well, probably the one tree was instrumental in causing a certain amount of coverage. So a tree-level mutation is going to keep the coverage that I had before in some sense, but then make some variation to it. Whereas if I mutate the source of randomness, I could get a completely different data structure the next time I run. So it's unclear that you're retaining as much prior information as you might like to when you mutate the source of randomness, because you're just going to end up generating potentially very different inputs. And so there's actually a paper that just appeared at ISTA, this Zest paper, that uses the Crowbar approach. And they find that it does work better than purely random testing. When we purely random property testing, when we compare Crowbar against our system in this work, in Fuzz Check, we find that it's not very much better, at least for these two benchmark cases, than random testing. And our hypothesis is the reason I just gave you. Another thing that's nice about Zest, or about this other, another thing that's nice about Zest, in addition to it using the mutation of the randomness approach, is that it can tell the difference between discarded and non-discarded runs. So normal fuzzers, you can't tell the difference when Acrobat Reader rejects your input as being ill-formed from it is unhappy with your perfectly well-formed input for some other reason. Or that it actually succeeds and just returns normally. There's no way to tell the difference between those two out of the box. AFL basically says if it terminates normally, that's fine. If it doesn't terminate normally and it's a crash, that's cool, that's a bug. But all the terminate normally cases, whether it's for rejecting the input or properly processing the input, it can't tell the difference. And so therefore there's no notion of a discarded run, that is a run that didn't satisfy the precondition. So what Zest does is Zest is able to instrument the target programs to know once you've gotten past the semantic checking phase and you've noticed that the input is well formed, awesome. Now that if that program terminates, I know it's sort of an acceptable run as opposed to a discarded run. And what they find is that knowing the difference between discarded runs and acceptable runs does make a huge difference in terms of overall performance. So our approach does this as well. Okay, so here we are. Here we had naive random testing. There we have the handwritten generator. And here we have Fuzz Check, which is way better, but not exactly the same here. At least in our particular case, there was a tiny bit of writing that you had to do for creating your generator. And it is important for performance to be able to do that sometimes. So of course, now that we've done step one, you can immediately imagine, let's bring in all of the advances from fuzzing. Let's look at symbolic execution-based cases. Let's look at ones that involve a grammar, right? All of these advances that that improve on AFL, we could potentially bring into property testing as well. So who knows what that might look like. That'll be something that we work on next. We're also thinking about other ways to generate mutators. I didn't really talk at all about the complicated loop and deciding when should I do generation, when should I do mutation, which mutation should I do, how long should I do those two things, when should I discard the seeds. Right? There's lots of policies that you can imagine exploring that we haven't really done yet that might make a big difference. Same thing, there's a bunch of insights from the regular fuzzing community that could make sense there. Okay, so in summary, coverage-guided property-based testing is a combination, pretty straightforward combination of random testing and coverage-guided fuzzing. The key insight is the notion of a semantic mutation. The even more naive combination is the crowbar approach, and our improvement to that is to realize that semantic mutations are likely to do better. We implemented this in Fuzz Check and showed that it works well. And actually, one thing I should have mentioned that we're doing now is we have a whole corpus of other examples that we're working on to further evaluate this, basically to test those different scheduling strategies and so on. So, for example, we have a development of System F, and we're seeding your System F type checker and operational semantics with bugs, and seeing, can we find those bugs when trying to falsify type soundness. And I think that is all that I have. Yep. So thank you.
Professor, the coverage part is used only to decide whether you want to add this generated input into the seed pool or not. But other than that, if a new path is discovered, that coverage information is not being used in the mutation itself.
No, that's correct. It's just whether to keep it in the seed pool.
Yes.
Yeah.
That could contribute a lot to. I mean, it could direct the mutation plan.
So you would have to. So at the moment, the coverage information is really simple in order for it to be fast. All that it's doing. So the way that AFL works is it instruments the program. So we're using the AFL style coverage. The way it instruments the program so that there is a sort of a global variable that is a dynamically determined indicator of an edge in the control flow graph. And basically, every time you reach a basic block, there's a seeded number for that basic block, and the edge is kind of the XOR of those two things, and then that's thrown into a hash table to keep track of how often that edge is covered. So the upshot of this is we have no idea what that edge is actually doing inside of the program. And so knowing that there is that new edge doesn't tell us what about the input precipitated that new edge, what that part of the program is doing. So I think we would have to figure that out if we were to use the fact that it was that edge to decide what mutation to add. But that's an interesting idea. Maybe changing the way coverage works to be a little bit slower, but maybe a little smarter, communicating more information could help.
That sounds like something like Sage, right?
It does actually, yeah, that's right. It's basically what a symbolic executor would do.
Oh, yeah, correct.
Ken?
So there's a lot of work on sampling out of constrained spaces, like trying to do uniform sampling out of some Boolean formula or something like that. Is any of that useful? Is it just too slow to apply in a testing framework?
So you're thinking that precondition on the left-hand side, that's a state space. Can I sample out of that state space?
Right. There are techniques you could use to sample out of that space uniformly.
I don't know. That's an interesting idea.
Also, so these programs that you're testing are effectively taking a single input and producing an output. So has this kind of technique been used in anything, for any kind of reactive program? Something where you put in an input, you get an output, and you have to respond with another input, and so forth. Can you imagine using a mutation-based technique for that?
So you can make your properties, they're still finite, but you could make your properties work that way. This is kind of to Emery's point, that you just then have a much longer you either have to break up the properties so that you're looking at some stepwise invariant that you're trying to test against, and so then you have multiple properties, maybe one considering the first step, one considering the second step, or you have to actually run multiple steps, which then slows down your testing time. So my suspicion is that most of the random testing work is for as quick as possible properties that might be for a reactive system, but they're sort of unit testing elements of that system that rather than looking at the actual sort of end-to-end performance of that thing. And I think that's just because the testing works better when the tests run as fast as possible.
What I'm imagining is, you get an output and you have to produce a responsive input. Right? The precondition will depend on the previous output. So now, if I had my previous test, it might be that a mutation of that previous second input is not useful, because the new output that I got is completely different.
I mean, it's in some ways, the way that I'm thinking of it is that you're saying so it's a stateful system, and then the output implies sort of that the next input is going to be processed under that new state. So I could translate that into a single property by including in my precondition, the system is in at this state, here's the input, what happens. I have another property, the system is in this state, here's the input, what happens. And I break it up that way. I imagine what happens is, that's what property testing, people who use property testing are doing, is they're thinking about those different states, they're adding them to the precondition. So I could take an idea from your suggestion, which is, hey, could I have even a higher level property, which is about the system as a whole, and could I break it into parts that I could test individually in order to make it quick?
There's another question over there, Emery.
Yeah, so I have a random meta question. Since we're talking random all the time. So, I know this is in the context of theorem provers and so on, but it seems like there could be some sort of guidance, in a sense, from the way fuzz testing is used to how programmers write code. So have you thought about that? Like, here's a methodology for writing code or producing APIs or something that would make them more amenable to fuzzing.
That's interesting. I'm a little bit reminded of, I don't remember the name, where this paper came from. So one problem with building resilient systems is that when you have lots of components that have sparse preconditions, and you think that this invariant is being satisfied, and some component of the system is not doing it. And so locally, those components are not resilient. I assume my inputs are always non-null. I assume that it's this number that's within this range, and I just take on faith that that's true. And if I get something that's not that way, then the whole thing falls apart. So you could imagine writing systems that were not that way, that you did redundant null checks because you didn't trust yourself, you didn't fully formally prove the system to see whether or not your inputs do satisfy the precondition you had otherwise been assuming. Certainly if you did that, that would make fuzz testing easier because it would make it so that more inputs would be acceptable to those functions in the program. Oh, but now that I say that, they're not going to be interesting because then they're just going to be discarded right away once you enter the function. Yeah, I don't know. I don't have any good ideas other than that bad idea.
Yeah.
So you mentioned that you're working now on kind of doing this thing for type systems and trying to falsify type safety. Are you hopeful this would be a great thing to have? Are you hopeful that you'll be able to satisfy these perhaps stronger preconditions? Or I guess to rephrase the question, how does the precondition that you had for this thing compares in terms of difficulty or whatever? Would say this program is well typed.
So it depends. So we did a case study with the simply typed lambda calculus, and we found this is a good thing, but it's a little disappointing for us, that totally random testing was fine. That for simply typed lambda calculus, it was actually easy to generate terms that were well typed right from the beginning, and you could very quickly find the bugs. I mean, it wouldn't be nanoseconds, but it would be 8 seconds or something like that. It would find the bug. Now, for System F, that's not true. It's much harder to generate stuff that's a well-typed System F term that will catch like wacko de Bruijn indices, errors, or things like that you could very easily make. And so in that case, the random tester is garbage. We're still in the process of evaluating whether our technique is better than garbage. It seems like it is. Could we do more than System F? If we did the whatever the name of that calculus is that you work on for Scala, yes, exactly. I don't know. I mean, I think that's where we're headed. I would like for that to be the case, and those are certainly going to be case studies that we use going forward.
Yeah.
So, in the 33 bug samples that you showed us, those were bugs that you had generated, right? So have you done any analysis of whether those bugs were things that you were likely to actually encounter in the real world?
Right. So Leo, the first author, wrote those systems and did those proofs, participated a lot in the proofs, and could attest that some of those bugs were bugs that were in the system. So they did this paper in 2013. That's where the handwritten generator came from. They started doing this testing stuff then because they realized, gosh, we're introducing these bugs. We keep trying to do the proofs. They're not working. I wonder if we could do testing to find these bugs. So many of those bugs in that list were actual bugs that have happened before. And then we were trying to be systematic in how to produce those bugs. I don't know if somebody else doing the proof might have produced one of the other bugs or not. It's a single person case study. We did a little bit of work looking at student written interpreters for my programming languages class where they have bugs. But unfortunately, we had the same problem as simply type lambda calculus, that this interpreter was not sophisticated enough that coverage guidedness provided any advantage, that normal random testing just was, it could satisfy those preconditions well enough that even with real student bugs, normal random testing would just find them. So ideally, what you would do is you would be able to test on things that were interesting in the real world, like these real bigger programming languages you're trying to prove stuff about, and then you could test them on real bugs, and hopefully we'll get to that. I just don't know how many examples there might be.
I'm wondering if this could be applied to QuickCheck itself rather than on Coq. It's a bigger community of people doing QuickCheck.
So for sure, the reason that we did it in QuickCheck was purely pragmatic, and that is there is a OCaml compiler extension that adds the AFL style coverage, and we could therefore do this comparison against Crowbar directly, and we could also extract the Coq code to OCaml and then instrument that extracted code. If we did it for QuickCheck, we would need an instrumenter for Haskell programs to add all this coverage information, and that might also be, maybe that would be cool, but it would be a little interesting given that Haskell is lazy as well, what that would mean. Maybe that doesn't make any difference. There just isn't one of these instrumenters, so it was a pragmatic choice.
Let's thank Mike again.
Was
there one?
I was just going to make one comment. So I work with Erlang QuickCheck primarily.
Oh, okay.
And so I believe, Erlang has a built-in, you can do it distributed and non-distributed, and you can get coverage while you're running the test. And we actually use this to run QuickCheck in a distributed mode and then aggregate the coverage. So you would have that facility there.
Great. Okay. Well, then we should try that.
Yeah. So that might be another alternative to Haskell.
Send me an email.
I will.
Great. Thank you.
Great. I'm glad I waited for that. All right. Let's thank Mike again.
All right.